4.5 billion years compressed into an hour. That's what we're doing here. Every mountain that rose and fell, every ocean that formed and dried, every creature that lived and died, all of it flowing past us at roughly 75 million years per minute. By the time you finish watching this, you'll have witnessed the entire lifespan of our planet, from a molten hellscape to the world spinning beneath your feet right now. Let's start at the absolute beginning. Picture this. There is no Earth. Not yet. Just a swirling disk of gas and dust orbiting a newborn star we'll eventually call the Sun. This disk is leftovers from the star's formation, and it's spinning fast. Gravity starts pulling particles together. Dust grains stick to other dust grains. Those clumps attract more material. Over millions of years, these growing masses smash into each other, sometimes merging, sometimes shattering apart. This violent game of cosmic bumper cars continues until something substantial begins to take shape. Around 4.5 billion years ago, one of these planetary embryos grows large enough that we can call it proto-Earth, but calling it Earth would be generous. This thing barely resembles the planet you know. Its surface is an ocean of molten rock, glowing red and orange like the inside of a furnace. There's no solid ground, no water, definitely no life. The temperature hovers around 2,200 degrees Fahrenheit. Asteroids and comets constantly slam into the surface, each impact releasing enough energy to vaporize rock instantly. The atmosphere, if you can even call it that, is a toxic soup of hydrogen, helium, and vaporized metals. This is the Hadean Eon, named after Hades, the Greek underworld. The name fits perfectly. For tens of millions of years, this is just how things are. Earth is a growing ball of violence and heat, slowly accumulating mass from everything unlucky enough to cross its path. Then something happens that changes everything. There's another planet-sized object out there, orbiting the same young sun. Scientists call it Theia, named after the Greek Titan, who gave birth to the moon goddess. Theia is roughly the size of Mars, and its orbit is unstable. The math of gravity and momentum has been pulling these two bodies closer for millennia. Around 4.4 billion years ago, they finally meet. The impact is beyond comprehension. Theia doesn't just graze Earth or create a crater. It slams into the planet at an angle, hitting with such force that both objects partially vaporize on contact. Imagine two massive water balloons colliding, except instead of water, they're filled with molten iron and rock heated to tens of thousands of degrees. The collision sends enormous plumes of debris spiraling into space. Earth's rotation speeds up dramatically. The entire planet rings like a bell struck by a cosmic hammer. Most of Theia's core merges with Earth's, sinking toward the center due to its density. But the lighter materials, the rocky mantles of both worlds, get ejected into orbit. This debris forms a ring around Earth, similar to what you'd see around Saturn, but made of vaporized rock instead of ice. Over the next few thousand years, this ring gradually coalesces. Gravity pulls the material together, and within a relatively short time, Earth has a companion, the Moon. This isn't just some random celestial event. The Moon's formation fundamentally shapes everything that comes after. Its gravitational pull stabilizes Earth's rotation, preventing wild wobbles that would make the planet nearly uninhabitable. It creates tides that will eventually play a crucial role in the evolution of life. Right now, though, the Moon is much closer than it is today, orbiting only about 15,000 miles away compared to the current 239,000. From Earth's surface, if there were anyone to see it, the Moon would appear enormous, dominating the sky and creating tides hundreds of feet high. But we're getting ahead of ourselves. There's still no surface to stand on. The heat from the Theia impact keeps Earth molten for millions more years. Slowly, agonizingly slowly, the planet begins to cool. The bombardment of asteroids and comets continues, but gradually decreases as the solar system cleans itself up. By around 4.4 billion years ago, something remarkable happens. The surface temperature drops enough for the first solid crust to form. It's not stable, not yet. Think of it like the skin that forms on hot chocolate when it cools. Thin, fragile, constantly breaking apart and reforming. Volcanic activity is everywhere and constant. Lava flows across vast stretches of the surface, only to cool and harden before the next eruption breaks through. But it's a start. For the first time, Earth has something resembling a solid surface, even if that surface is constantly being destroyed and rebuilt. Around this time, another crucial development occurs. Water arrives. Where does it come from? Scientists still debate this, but the most likely answer is comets and asteroids. These icy bodies, loaded with frozen water, have been pummeling Earth throughout the Hadean. Most of that water instantly vaporized on impact due to the extreme heat. But as the surface cools below the boiling point of water, around 212 degrees Fahrenheit, at sea level, the water vapor in the atmosphere can finally condense. It starts to rain, and it rains, and it rains, and it rains. This isn't a gentle spring shower. This is a torrential downpour that lasts for millions of years. Water falls from the sky in sheets, pools in the low areas, evaporates back into the atmosphere, and falls again. The cycle repeats endlessly. Gradually, the low-lying basins fill up. By around 3.8 billion years ago, Earth has its first oceans. They're hot, acidic, and nothing like the blue waters you'd recognize today. The ocean water is probably greenish or even reddish due to dissolved minerals. The sky's likely orange or pink from all the volcanic gases, but they're oceans nonetheless. Now, Earth has three fundamental ingredients that will matter enormously in just a few 100 million years: liquid water, a solid surface, and an atmosphere. The planet is still hostile beyond imagination, but it's no longer just a ball of molten chaos. It's becoming something more organized, more structured. The stage is being set. Volcanic islands begin to emerge from the primordial oceans. These aren't like the volcanic islands we see today. They're smaller, more numerous, and incredibly unstable. The early crust is thin, maybe only a few miles thick in places. Magma breaks through constantly, creating new islands while swallowing old ones. Tectonic activity is far more violent than anything modern Earth experiences. The continents as we know them don't exist. Instead, there are scattered protocontinents, small patches of lighter rock that float on the denser oceanic crust like scum on a pond. The atmosphere is still toxic. Carbon dioxide levels are astronomical, creating a greenhouse effect that keeps temperatures around 200 degrees Fahrenheit, even though the sun is about 30% dimmer than it is today. There's almost no oxygen. Breathing this air would kill you in seconds. The sky is thick with clouds, and lightning constantly arcs between them. The young Earth is loud, violent, and utterly alien. Yet something is about to happen in these harsh conditions that will change everything. Something so improbable, so extraordinary, that we still don't fully understand how it occurred. Somewhere in these primordial oceans, probably near volcanic vents on the seafloor where heat and chemicals mix in just the right proportions, chemistry becomes biology. Simple organic molecules start forming chains. These chains begin copying themselves. After millions of years of chemical experimentation, something crosses the threshold from complex chemistry to primitive life. The first living thing on Earth is almost certainly a single-celled organism, probably similar to modern bacteria, but even simpler. It has no nucleus, no complex internal structures, just a membrane holding together a few molecules capable of self-replication. This organism doesn't think, doesn't move intentionally, doesn't do anything we'd recognize as living except one crucial thing. It makes copies of itself. This happens around 3.8 to 3.5 billion years ago, though pinpointing the exact moment is impossible. We're talking about microscopic events in a violent ocean on a hostile planet. No one is there to record it. The evidence we have comes from tiny chemical signatures in some of Earth's oldest rocks, formations in Australia and Greenland that show possible traces of biological activity. But the evidence is ambiguous, controversial, and constantly debated. What we do know is this: by 3.5 billion years ago, life is definitely here. Microbial mats, dense carpets of bacteria-like organisms, grow in shallow waters. These mats build structures called stromatolites, layered mounds of sediment trapped and bound by the microbes. We can find fossilized stromatolites from this era, and remarkably, living stromatolites still exist in a few places today, virtually unchanged for over 3 billion years. But here's what makes this moment so pivotal. One particular type of organism evolves a trick that will eventually transform the entire planet. These organisms figure out how to harvest energy from sunlight through a process that releases oxygen as a waste product. We call this photosynthesis, and these early practitioners are ancestors of modern cyanobacteria. At first, the oxygen doesn't accumulate in the atmosphere. The oceans are full of dissolved iron and other materials that react with oxygen immediately, soaking it up like a sponge. For hundreds of millions of years, these oxygen-producing organisms are essentially pumping out a waste product that vanishes instantly into chemical reactions. The rust-colored bands in ancient rock formations, called banded iron formations, are the remnants of this process. The oxygen combined with dissolved iron, which then precipitated out and settled on the ocean floor. Around 2.4 billion years ago, something shifts. The oceans have finally absorbed about as much oxygen as they can through chemical reactions. The sponge is saturated. Oxygen begins accumulating in the atmosphere itself, slowly at first, then faster. This event, called the Great Oxidation Event, is one of the most dramatic changes in Earth's entire history, and it's about to cause the first mass extinction. For most organisms alive at the time, oxygen is poison. Think about that for a moment. The very gas you're breathing right now, the molecule that keeps you alive, would have been lethal to almost everything living on early Earth. These ancient microbes evolved in a world without oxygen. Their chemistry is built around its absence. When oxygen starts accumulating in the atmosphere, it tears through their cellular machinery like acid. It's toxic, reactive, deadly. The Great Oxidation Event is really the Great Oxidation Crisis. Entire ecosystems collapse. Species that dominated the oceans for hundreds of millions of years are suddenly choking on their own planet's changing atmosphere. Some organisms retreat to the few remaining oxygen-free zones, deep mud, stagnant pools, the guts of other creatures. Their descendants still live there today, clinging to the chemistry of an ancient world, but most simply go extinct. This is Earth's first mass die-off, caused not by an asteroid or a volcano, but by life itself. Organisms that figured out how to use sunlight poisoned the atmosphere for everything else. Yet this catastrophe opens a door. Oxygen is reactive, yes, but that reactivity is also useful. It can break down molecules and release energy far more efficiently than the chemical processes available before. Organisms that can tolerate oxygen, or better yet use it, suddenly have access to an incredible power source. Evolution doesn't plan ahead. It doesn't see the potential. But random mutations that help organisms survive in this new oxygen-rich world get passed on. Slowly, new forms of life emerge, forms that breathe oxygen, that need it. Life adapts. It always does. For the next billion years, Earth remains a microbial planet. Bacteria and single-celled organisms dominate. They live in the oceans, in hot springs, in shallow pools. They form vast mats and colonies. They evolve slowly, experimenting with different chemical pathways, different survival strategies. The planet itself continues changing. Continents drift. Oceans shift. Ice ages come and go. But nothing truly dramatic happens in terms of complexity. Life stays small and simple. Then, around 1.5 billion years ago, something remarkable occurs inside a single-celled organism. One cell engulfs another, but instead of digesting it, the two form a partnership. The engulfed cell, probably something like a bacterium, starts living inside the host cell permanently. Over time, this internal resident becomes an organelle, a specialized structure called a mitochondrion. It handles energy production for the host cell. This process, called endosymbiosis, happens more than once. Another engulfed cell becomes a chloroplast, enabling photosynthesis. These merged cells are the ancestors of all complex life on Earth. Every plant, animal, fungus, every organism with cells containing a nucleus traces back to these ancient partnerships. This is the origin of eukaryotic cells, and it's a prerequisite for everything that follows. But even after eukaryotic cells appear, life stays mostly single-celled for another billion years. Why the delay? We don't know. Maybe oxygen levels need to rise further. Maybe certain genetic innovations are required. Maybe it's just timing, random chance in an ocean of possibilities. Around 600 million years ago, something shifts. Multicellular organisms start appearing. Not just colonies of identical cells clumped together, but organisms with different cell types working together. Cells specialize. Some become structure, some become sensors, some handle digestion. These early multicellular organisms are soft-bodied, weird, unlike anything alive today. We call them the Ediacaran biota, named after the Australian region where their fossils were first found. They look like quilted pancakes, fronds, and strange segmented tubes. They don't have mouths, eyes, or obvious ways of moving. They seem to absorb nutrients directly through their surfaces. For about 30 million years, these bizarre organisms dominate the ocean floor. Then they mostly vanish. What replaces them is explosive. Around 541 million years ago, at the start of the Cambrian period, life goes absolutely wild. In a span of just 10 to 20 million years, an eye blink in geological terms, nearly all major animal body plans appear. This is the Cambrian explosion, one of the most dramatic events in evolutionary history. Suddenly, the oceans are full of creatures with hard shells, eyes, claws, segmented bodies, complex nervous systems. Trilobites scuttle across the seafloor. Anomalocaris, a nightmare predator nearly a meter long with grasping appendages and circular jaws, hunts smaller creatures. Worms burrow into the mud. Sponges filter water. Creatures with 5 eyes or limbs in bizarre configurations, or body plans that don't fit any modern category, all appear and compete. Why does this happen? Several factors probably combine. Rising oxygen levels finally reach a threshold that supports larger, more active bodies. The evolution of predation creates an evolutionary arms race. Better armor, faster movement, sharper senses. Once one organism develops eyes, everything else needs to respond. The genetic toolkit for building complex bodies, genes that control how and where body parts form, reaches a level of sophistication that allows rapid experimentation. And maybe there's just empty ecological space, niches waiting to be filled. Whatever the cause, the results reshape the planet. Life is no longer just background chemistry. It's visible, active, interactive. Ecosystems become complex webs of predators and prey, filter feeders and scavengers. Reefs form from the calcium carbonate structures built by early corals and sponges. The ocean floor, once mostly barren mud, becomes a crowded, competitive environment. But all of this is still underwater. The land remains essentially lifeless. Barren rock, sterile sand, no plants, no animals, nothing. Just stone baking under an unfiltered sun. That's about to change too. Around 470 million years ago, simple plants, probably resembling modern mosses, begin colonizing the edges of water. They're small, fragile, clinging to moist rocks, but they're the pioneers. By 400 million years ago, true vascular plants, with systems for moving water and nutrients, spread inland. Forests of bizarre plants, some looking like giant ferns, others like towering stalks covered in scales, begin covering the continents. These aren't trees as we know them. Many don't have leaves. Their internal structure is alien, but they're plants, and they're turning the land green for the first time in Earth's history. Where plants go, animals follow. Arthropods, relatives of modern insects and spiders, crawl out of the water. At first they stay near shorelines, but gradually they venture further. Some grow large. Millipedes a meter long, scorpions the size of dogs, dragonflies with wingspans approaching a meter. The high oxygen levels during this period, sometimes reaching 35% compared to today's 21%, allow insects and other arthropods to grow to sizes that would be impossible now. Vertebrates, animals with backbones, also make the transition. Early fish develop lungs and sturdy fins that can support weight. These lobe-finned fish start hauling themselves onto mudflats, probably to escape predators or reach new food sources. Over millions of years, fins become legs, gills become lungs. Around 365 million years ago, the first tetrapods, four-limbed vertebrates, are walking on land. They're still tied to water, needing it for reproduction, but they're out. Life has conquered a new realm, and then the planet tries to kill everything again. Around 252 million years ago, at the boundary between the Permian and Triassic periods, Earth experiences the worst mass extinction in its history. More than 90% of marine species die. Around 70% of land vertebrate species vanish. This is the Great Dying, and it nearly ends complex life entirely. The cause is likely massive volcanic eruptions in what's now Siberia. These eruptions last for thousands of years, pumping out enormous quantities of lava, ash, and greenhouse gases. The climate goes haywire. Oceans acidify and lose oxygen. Temperatures spike. Food chains collapse. For a few million years, ecosystems are devastated, reduced to a handful of surviving species struggling in a hostile world. Recovery is slow, but life, as always, finds a way. And what emerges from this catastrophe will dominate the planet for the next 186 million years. The age of reptiles is about to begin. Actually, we need to be more specific. The age of dinosaurs. The Triassic period begins in a graveyard. Ecosystems are skeletal. The few survivors are small, opportunistic, adaptable. Many are reptiles. Some of these reptiles have evolved a crucial advantage, an upright stance. Instead of legs splayed out to the sides like a lizard, their legs are positioned directly beneath their bodies. This makes them faster, more efficient, better at covering ground. These are the archosaurs, the ruling reptiles. And from this group, two major lineages emerge. One will become crocodiles, the other will become dinosaurs. The first dinosaurs appear around 230 million years ago. They're not impressive. Small, bipedal, maybe the size of a dog. They're not dominant. Early Triassic ecosystems are actually ruled by other reptiles, some resembling mammals, others looking like bizarre armored pigs. Dinosaurs are just one player among many, but they have potential. Over the next 30 million years, something shifts. Competitors die out. Environmental conditions favor certain traits. Dinosaurs begin diversifying, growing, spreading. By the start of the Jurassic period, 201 million years ago, they're the dominant land animals on every continent, and they stay dominant for an almost incomprehensible stretch of time. 135 million years of uninterrupted rule. Think about that. Humans, modern humans, have been around for maybe 300,000 years. Recorded history covers about 5,000 years. Dinosaurs ruled for 135 million. They weren't just one thing either. Herbivores the size of buildings, carnivores with teeth like steak knives, armored tanks with spiked tails, swift runners, gliders, eventually flyers. The sheer variety is staggering. Take the sauropods. Long necks, long tails, massive bodies supported by pillar-like legs. Brachiosaurus, Diplodocus, Argentinosaurus, possibly the largest land animal ever, maybe weighing 100 tons. These creatures couldn't run. They didn't need to. Their size was their defense. An adult sauropod had no predators. None. They moved in herds, stripping forests bare, reshaping landscapes just by existing. Then there's the theropods, bipedal carnivores. This group includes some of the most famous dinosaurs. Allosaurus, apex predator of the Jurassic. Velociraptor, smaller than movies suggest, but vicious pack hunter. And Tyrannosaurus rex, the icon, appearing near the very end of the age of dinosaurs. Rex wasn't the biggest carnivore ever. Spinosaurus might have been larger, but Rex was possibly the most powerful bite force of any land animal in history. Bone-crushing jaws capable of tearing through armor. A predator so effective, it may have had no real competition, but dinosaurs weren't all monsters. Some were delicate. Compsognathus, chicken-sized, darting through underbrush hunting insects. Microraptor, a small theropod with feathers on all four limbs, gliding between trees. Yes, feathers. Not all dinosaurs were scaly. Many, especially smaller theropods, were feathered, fluffy even. This changes how we imagine them. The image of a T-Rex covered in proto-feathers, especially as a juvenile, is strange. But it's accurate. Dinosaurs dominated land, but they didn't rule everywhere. The oceans belonged to other reptiles. Ichthyosaurs, dolphin-shaped marine reptiles. Plesiosaurs, long-necked swimmers. Mosasaurs, massive marine lizards appearing later, apex predators of the Cretaceous seas. And the skies weren't controlled by dinosaurs either. Pterosaurs, flying reptiles, some with wingspans exceeding 10 meters, soared above. These weren't birds. They weren't even dinosaurs. They were a separate lineage, equally successful, equally strange. Birds, however, are dinosaurs. They evolved from small theropods during the Jurassic. Archaeopteryx, one of the earliest known birds, appears around 150 million years ago. It has feathers, wings, and a wishbone. It also has teeth, a long bony tail, and clawed fingers. It's a perfect transitional form. Over millions of years, birds diversify, lose their teeth, refine flight. By the end of the Cretaceous, recognizable modern bird groups exist. When the dinosaurs fall, birds survive. They're the only dinosaur lineage that makes it through. The Cretaceous period, the final chapter of the Mesozoic, is a time of incredible diversity. Flowering plants, angiosperms, appear and spread rapidly. Dinosaurs co-evolve with them. Ceratopsians, horned dinosaurs like Triceratops, develop complex chewing mechanisms to process tough plant material. Hadrosaurs, duck-billed dinosaurs, evolve elaborate crests and social behaviors. Ankylosaurs, perfect body armor, becoming living tanks. The world is full, crowded, thriving. And then, 66 million years ago, everything ends. An asteroid, roughly 10 kilometers wide, slams into what's now the Yucatan Peninsula in Mexico. The impact releases energy equivalent to billions of atomic bombs. The immediate destruction is catastrophic. Everything within hundreds of kilometers is vaporized. Shockwaves flatten forests across continents. Tsunamis hundreds of meters high scour coastlines. But the real killer isn't the impact itself. It's what comes after. Debris is thrown into the atmosphere. Dust, ash, vaporized rock. It spreads globally within hours. The sky goes dark. Photosynthesis stops. Temperatures plummet. This is impact winter. Plants die. Herbivores starve. Carnivores with nothing to hunt follow. The food chain collapses from the bottom up. Smaller animals, those that can survive on seeds, carrion, insects make it. Anything large, anything requiring substantial daily food intake, dies. 75% of species go extinct. Every non-avian dinosaur vanishes. Pterosaurs gone. Most marine reptiles gone. Many plants gone. The planet is devastated, but not sterilized. Life persists, and in the wreckage, opportunity emerges. Mammals have been around almost as long as dinosaurs. They appeared in the Triassic, small, nocturnal, living in the shadows. For 160 million years, they stayed small. Dinosaurs occupied the large-bodied niches. Mammals couldn't compete. But now the dinosaurs are gone. The niches are empty. And mammals, adaptable, warm-blooded, capable of surviving on varied diets, are perfectly positioned to fill them. Within a few million years, a blink in geological time, mammals explode in diversity. They grow. Some become grazers. Others become browsers. Predators evolve. Within 10 million years of the extinction, there are mammals the size of bears. Within 25 million years, some are the size of elephants. The Cenozoic era, the age of mammals, is underway. Early Cenozoic mammals are strange. Uintatherium, a rhinoceros-sized herbivore with bony horns and saber-like canines. Andrewsarchus, possibly the largest terrestrial carnivorous mammal ever, built like a wolf but the size of a bear. Indricotherium, a hornless rhino relative, standing over 5 meters tall at the shoulder, the largest land mammal in history. These aren't the mammals we know. They're experiments, evolutionary trials. Primates appear early in the Cenozoic, small tree dwellers. Over tens of millions of years, they diversify. Some stay small, others grow. Around 25 million years ago, apes split from monkeys. Around 7 million years ago, the human lineage splits from chimpanzees. Our story, the story of hominins, begins. Early hominins are upright walkers, but still small-brained. Australopithecus, appearing around 4 million years ago, walks on 2 legs, but has a brain only slightly larger than a chimp's. Tool use begins. Fire is controlled. Brain size increases. Homo erectus, appearing 1.9 million years ago, spreads out of Africa into Asia and Europe. This is the first hominin to truly explore the world. Then, around 300,000 years ago, Homo sapiens appears in Africa. Anatomically modern humans. We're not alone. Neanderthals exist in Europe and the Middle East. Denisovans in Asia. Other hominin species in isolated pockets. But we're different. Our brains are wired for abstract thought, complex language, symbolic culture. We make art. We bury our dead. We tell stories. Around 70,000 years ago, a small population of Homo sapiens leaves Africa. This group, maybe just a few thousand individuals, will populate the entire world. By 50,000 years ago, humans are in Australia. By 15,000 years ago, we're in the Americas. We adapt to every environment: deserts, rainforests, tundra, mountains. We hunt megafauna to extinction in many regions. Mammoths, giant sloths, marsupial lions. Within a few thousand years of human arrival, they're gone. Then, 12,000 years ago, we invent agriculture. This changes everything: permanent settlements, population growth, division of labor, civilization. Writing appears 5,000 years ago. Empires rise and fall. Technology accelerates. And here we are, 200,000 years of human history. A blip, a fraction of a percent of Earth's story. But our impact is enormous. We've altered the climate, reshaped landscapes, driven species extinct at rates matching past mass extinctions. We've become a geological force. The Anthropocene, some call it. The age of humans. Whether this age lasts millions of years or ends abruptly depends entirely on what we do next. So what happens next? We've reached the present. But Earth's story doesn't end here. The planet keeps spinning. Continents keep drifting. The sun keeps burning. And time, indifferent to our existence, marches forward. Let's step into the future, not decades or centuries, but millions, even billions of years ahead. What does Earth become when we're gone? Start with the near future. Geologically speaking, the next few million years. Continents are still moving. Africa pushes into Europe, slowly closing the Mediterranean Sea. In perhaps 10 million years, the Mediterranean could become a mountain range, a new collision zone like the Himalayas. Australia drifts north toward Asia. The Pacific Ocean shrinks. The Atlantic widens. These are slow processes, millimeters per year, but over deep time, they reshape the world entirely. Around 50 million years from now, something else happens. Africa fully collides with Europe. The Mediterranean is gone, replaced by a massive mountain chain stretching from Spain to the Middle East. Australia merges with Southeast Asia. The Pacific continues to close. The Atlantic keeps expanding. Earth's face is unrecognizable compared to today, but the real transformation comes later. Around 250 million years in the future, the continents converge again. Just as they did to form Pangaea 300 million years ago, they'll do it again. This new supercontinent has a name already, hypothesized by geologists: Pangaea Ultima. All landmass fused into one colossal shape, surrounded by a single global ocean. The interior of Pangaea Ultima will be brutal. Imagine the most extreme desert on Earth today, then amplify it. Thousands of miles from any coastline, no moisture penetration, baking under relentless sun. Temperatures in the interior could regularly exceed 140 degrees Fahrenheit, uninhabitable for most complex life. The coasts might support ecosystems, but the heart of the continent, a sterile wasteland. And it's not just heat. The configuration of continents affects ocean currents, atmospheric circulation, climate stability. Pangaea Ultima could trigger extreme climate swings, massive storms, prolonged droughts. Volcanic activity along the suture zones where continents merge would release carbon dioxide, potentially warming the planet further. Life would adapt, as it always does, but it would be stressed, constrained, pushed to the edges. But there's something else happening simultaneously, something far more ominous. The moon is leaving us. Right now, the moon is drifting away from Earth at about 1.5 inches per year. It's been doing this since it formed. The rate isn't constant. It varies depending on tidal dynamics, but the trend is clear. The moon is slowly escaping Earth's gravitational embrace. In 250 million years, it will be noticeably farther away. In 1 billion years, much farther. And as it recedes, Earth loses stability. The moon stabilizes Earth's axial tilt. Right now, Earth's axis tilts at about 23.5 degrees, giving us seasons, stable climate zones, predictable weather patterns. Without the moon's gravitational influence, that tilt could vary wildly over time, swinging from near zero to over 45 degrees. Imagine the consequences. If the tilt dropped to near zero, there would be almost no seasons. Equatorial regions would bake year-round, poles would freeze permanently. If the tilt increased to 45 degrees, summers would be extreme, winters brutal, and temperate zones would vanish. Climate chaos. Ecosystems unable to adapt fast enough. Mass extinctions. The moon's slow departure doesn't just destabilize the tilt, it also slows Earth's rotation. Right now, a day is 24 hours, but Earth's rotation is gradually slowing due to tidal friction with the moon. In a few 100 million years, days could be 25 or 26 hours long. In 1 billion years, maybe 30 hours. Longer days mean more extreme temperature swings between day and night, more intense heating on the day side, more severe cooling at night. This stresses ecosystems further. Now let's jump ahead. Not 250 million years, but 1 billion. 1 billion years into the future. The sun is the problem now. Stars age. As they burn hydrogen in their cores, they gradually get hotter and brighter. The Sun has been doing this since it formed 4.6 billion years ago, and it will continue. In a billion years, the Sun will be about 10% brighter than it is today. That doesn't sound like much, but it's catastrophic for Earth. 10% more solar radiation means Earth heats up. The oceans begin to evaporate faster. Water vapor is a greenhouse gas, so more of it in the atmosphere traps more heat, which causes more evaporation, which traps more heat. A runaway greenhouse effect. The same process that turned Venus into a hellish 900-degree wasteland will begin on Earth. Temperatures soar. The oceans boil away. Within a few 100 million years, Earth's surface could be entirely dry. Water lost to space as ultraviolet radiation splits water molecules into hydrogen and oxygen, and the hydrogen escapes into the void. Without oceans, the carbon cycle breaks down. No water means no weathering of rocks, no sequestration of carbon dioxide. CO2 builds up in the atmosphere, further intensifying the heat. The surface becomes a scorched, barren rock. Any remaining life retreats underground, if it can. Microbes, perhaps, clinging to deep aquifers or geothermal vents. But complex life, gone. The age of animals, plants, fungi, everything we know, ends not with a bang, but with a slow, inexorable heating. But the Sun isn't finished. Not by a long shot. Fast forward again, 5 billion years from now. The Sun has exhausted the hydrogen in its core. It's been burning for 10 billion years total by this point, and the fuel is running out. When a star like the Sun runs out of core hydrogen, it begins fusing hydrogen in a shell around the core, and the core itself contracts and heats up. This causes the outer layers of the star to expand massively. The Sun becomes a red giant. Its outer envelope swells, growing hundreds of times its current size. It engulfs Mercury, then Venus, and then, possibly, Earth. Some models suggest Earth might just barely escape being swallowed, orbiting at the very edge of the Sun's expanded atmosphere. But even if Earth isn't physically consumed, it doesn't matter. The Sun's surface, now close enough to fill half the sky, radiates heat so intense that Earth's surface melts. Rock liquefies. The crust becomes an ocean of lava. The atmosphere, if any remains, is stripped away by the solar wind. Earth becomes a molten glowing ember, tidally locked to the dying Sun, one side eternally facing the inferno, the other a slightly cooler hellscape. Eventually, the Sun sheds its outer layers entirely, creating a beautiful planetary nebula, and what's left behind is a white dwarf. A dense, hot core about the size of Earth, slowly cooling over trillions of years. Earth, if it still exists, orbits this white dwarf as a dead, charred rock. No atmosphere, no water, no life. Just a cold, dark cinder in an empty system, illuminated only by the dim light of a fading stellar remnant. But here's the thing. Earth's story, in the grand scheme, is just one story. The universe is full of planets, billions upon billions of them. Some will meet similar fates. Others will persist longer, orbiting smaller, longer-lived stars. Some might never develop life at all. Others might develop life far more advanced than anything Earth has seen. Earth is not special in the universe. It's one experiment among countless others. And yet, for us, it's everything. Every human who has ever lived, every civilization, every war, every discovery, every love, every loss happened here, on this rock, in the thin layer of atmosphere clinging to its surface. Carl Sagan called it the pale blue dot. From a distance, that's all Earth is. A pale blue dot suspended in a sunbeam, insignificant on cosmic scales, yet the only home we've ever known. The future of Earth is written in physics. Continents will merge. The moon will drift. The sun will swell. These things are inevitable, barring some unknown intervention. But the future of life on Earth, at least in the near term, is not yet decided. We're here now, 200,000 years into our species' existence, And we have choices. We can continue altering the planet, driving extinctions, destabilizing the climate. Or we can adapt, preserve, protect what remains. The deep future, billions of years away, is beyond our control. But the next few centuries, those are ours to shape. And yet, here's what most people miss. Earth's story didn't start with green forests and blue oceans. It started with violence, pure, unrelenting chaos. Go back 4.5 billion years. There is no Earth yet, not as we know it. Just a cloud of dust and gas swirling around a newborn sun. Gravity pulls this material together, particle by particle, collision by collision. Slowly, a rocky core forms. But it's not done yet, not even close. This early proto-Earth is bombarded constantly. Asteroids, planetesimals, chunks of rock the size of cities, slam into the surface at thousands of miles per hour. Each impact releases energy equivalent to millions of nuclear bombs. The surface is molten, an ocean of magma glowing red and orange, radiating heat into the blackness of space. There's no sky, no atmosphere worth mentioning, just rock, fire, and violence. This is the Hadean Eon, named after Hades, the Greek underworld, because that's what it was, hell. Then, about 4.4 billion years ago, something catastrophic happens. A Mars-sized planet called Theia collides with Earth. Not a glancing blow, a direct hit. The impact is so violent that both planets are partially vaporized. Debris is flung into orbit. Some of it rains back down onto Earth. Some of it coalesces, forming a new body, the Moon. In a matter of hours, Earth gains a satellite, and the Moon from the very beginning starts influencing Earth's behavior. It stabilizes the planet's axial tilt. It creates tides. It slows Earth's rotation. Without the Moon, Earth would wobble chaotically, making stable climates nearly impossible. Life, as it eventually emerges, owes its existence in part to that ancient collision. But Earth isn't habitable yet. The surface cools slowly. Over millions of years, the magma ocean solidifies into a thin crust. Volcanic activity is relentless. Gases trapped in the interior, water vapor, carbon dioxide, nitrogen, ammonia, burst out through countless vents. These gases form the first atmosphere. It's toxic, unbreathable, but it's there. And then the rain begins. Not for days or weeks, for millions of years. Water vapor condenses in the cooling atmosphere and falls as rain, pooling in the low points of the newly formed crust. Slowly, the first oceans appear. By 3.8 billion years ago, Earth has liquid water. And where there's water, chemistry gets interesting. Somewhere, in some warm, shallow pool or deep-sea hydrothermal vent, molecules begin to organize. Simple organic compounds form, break apart, reform. Eventually, one molecule figures out how to replicate itself. That's it. That's the spark. Life. Not intelligent, not complex. Just a molecule that can copy itself. But it's enough. These early life forms are single-celled, simple beyond imagination. Bacteria, archaea, they don't need oxygen. In fact, oxygen is poison to them. They thrive in the anoxic oceans, feeding on chemicals dissolved in the water. For over 1 billion years, this is all life is. Single cells floating in the dark. Then, around 2.4 billion years ago, something changes. A group of bacteria evolves a new trick. Photosynthesis. They start using sunlight to convert carbon dioxide and water into energy, releasing oxygen as a waste product. At first, this oxygen doesn't accumulate. It reacts with iron dissolved in the oceans, forming rust that sinks to the sea floor. But eventually, the oceans can't absorb anymore. Oxygen starts bubbling into the atmosphere. This is the Great Oxidation Event. And it's a catastrophe for most life on Earth. Oxygen is toxic to the organisms that have dominated the planet for billions of years. They die off in massive numbers. but a few survive. And some of them adapt. They evolve ways to use oxygen for energy, which is far more efficient than anything that came before. This sets the stage for everything that follows. Fast forward to 541 million years ago. For billions of years, life has been mostly microscopic. Then, suddenly, everything explodes. The Cambrian explosion. In a geological blink, complex multicellular life appears. Trilobites, strange worm-like creatures with spines and legs, predators with compound eyes, shells, claws, teeth. The oceans become battlegrounds. Evolution accelerates. Within a few million years, nearly every major body plan that exists today has appeared. Why did this happen? No one knows for sure. Maybe oxygen levels finally reached a threshold. Maybe it was an evolutionary arms race. Predators evolved, so prey evolved defenses, so predators evolved better weapons. Whatever the cause, life becomes visible, complex, diverse, and then it crawls onto land. Around 450 million years ago, the first plants colonized the shore. Mosses, simple vascular plants. They transform the continents from barren rock into green landscapes. Insects follow, then amphibians. By 350 million years ago, forests cover the land. Giant ferns, trees 100 feet tall. And in these forests, the first reptiles appear. They lay hard-shelled eggs, which means they no longer need to return to water to reproduce. This is a game changer. Reptiles spread across the supercontinent Pangaea, diversifying into countless forms. Then, 252 million years ago, the worst mass extinction in Earth's history occurs. The Permian-Triassic extinction. Volcanic eruptions in what is now Siberia release massive amounts of carbon dioxide and sulfur dioxide. The climate destabilizes. Oceans acidify. Oxygen levels plummet. 90% of all species go extinct. The planet nearly dies. But life persists, and from the ashes, a new group rises. The dinosaurs. For 180 million years, dinosaurs dominate. They evolve into every ecological niche imaginable. Massive sauropods weighing 80 tons. Ferocious theropods like Tyrannosaurus rex. Armored herbivores. Flying pterosaurs. The Mesozoic era is their time. But then, 66 million years ago, an asteroid 6 miles wide slams into the Yucatan Peninsula. The impact releases energy equivalent to billions of nuclear bombs. Tsunamis hundreds of feet tall sweep across coastlines. Wildfires ignite across continents. Dust and debris fill the atmosphere, blocking out the sun for years. Photosynthesis stops. Food chains collapse. 75% of all species go extinct, including the dinosaurs, but not all of them. A small group of feathered theropods survives. We call them birds. And in the aftermath, with the dinosaurs gone, mammals seize the opportunity. For 160 million years, mammals had been small, nocturnal, living in the shadows of the dinosaurs. Now, they diversify. Within 10 million years, there are mammals the size of bears, then whales, then elephants. Primates appear, and eventually in Africa, a lineage of apes begins walking upright. 200,000 years ago, Homo sapiens emerges. Anatomically modern humans. For most of that time, we live in small groups, hunting, gathering, moving with the seasons. Then, 12,000 years ago, we figure out agriculture. Civilizations form. Writing, cities, empires. In the last 200 years, we've industrialized, split the atom, sent machines to other planets. On the timescale of Earth's history, we are a blip, a flicker, barely noticeable. And yet, in that brief moment, we've altered the planet in ways that will leave a mark in the geological record for millions of years. But Earth keeps moving, continents drift. In 250 million years, they'll merge again. Pangaea Ultima, a massive supercontinent centered near the equator. Most of it will be desert, uninhabitable. The climate will be extreme. Life will persist, but it will be different, unrecognizable. And the moon will be farther, its stabilizing influence weaker. Earth's axial tilt will vary more wildly, making climates chaotic. Then, 1 billion years from now, the sun brightens. Not much, just 10%, but it's enough. Temperatures on Earth rise, the oceans begin to evaporate. Water vapor in the atmosphere traps more heat, accelerating the process. Within a few 100 million years, Earth becomes Venus, a runaway greenhouse. Surface temperatures exceed 200 degrees Fahrenheit. Life, if it still exists, retreats underground or goes extinct entirely. The oceans are gone. The sky is thick with steam. And then, in about 5 billion years, the sun exhausts its hydrogen. It swells into a red giant. Its outer layers expand past Mercury, past Venus, possibly past Earth. Even if Earth survives being swallowed, its surface melts. The crust becomes lava. The atmosphere is stripped away. What remains is a dead, glowing rock orbiting a dying star. Eventually, the sun sheds its outer layers, leaving behind a white dwarf. And Earth, if it's still there, becomes a cold cinder in the dark. That's the story. From a molten hellscape to a pale blue dot teeming with life, and back to a barren rock. 4.5 billion years of geology, biology, catastrophe, and adaptation. Every mountain, every ocean, every species, temporary. Earth is not static. It never was. It's a dynamic, violent, beautiful system, constantly changing, constantly evolving. And we, humans, are just one chapter, a brief moment in a story that spans eons. But it's our moment, and what we do with it matters, at least to us. So what does all this mean? You've just watched 4.5 billion years unfold in an hour. Every second of this video represented roughly 1.25 million years of actual time. Empires that lasted centuries compressed into microseconds. Ice ages that shaped continents reduced to heartbeats. The entire span of human civilization, everything we've ever built or destroyed, barely registers as a flicker. It's easy to feel insignificant after seeing the full timeline. And in one sense, we are. Earth existed for over 4 billion years before the first human stood upright. It will continue long after the last one falls. The planet doesn't need us. It never did. We're passengers on a rock that's been through hell multiple times and kept spinning. We like to think we're masters of nature, but really, we're just the latest experiment in a laboratory that's been running since before the sun finished forming. But here's the paradox. Insignificant as we are on geological timescales, we're also unprecedented. In 4.5 billion years of Earth history, we're the first species to understand what Earth actually is. The first to know about plate tectonics, mass extinctions, the age of dinosaurs. The first to look up at the night sky and realize those aren't just lights. They're other suns, other worlds, entire galaxies, billions of light years away. The first to piece together this entire timeline from fragments of rock and bone. That counts for something. Maybe not to the universe, but to us, it should. Think about the improbability of you existing. Not just humans as a species, but you specifically. If the asteroid hadn't hit 66 million years ago, mammals would still be rat-sized creatures hiding from dinosaurs. If the Great Oxidation Event hadn't poisoned the atmosphere 2.4 billion years ago, complex life might never have evolved. If Theia hadn't collided with Proto-Earth, there'd be no moon to stabilize our climate. If any one of 1,000 variables had been slightly different, you wouldn't be here. None of us would. We're the product of countless catastrophes, accidents, and near misses stretching back to the formation of the solar system. And now we're making our own mark. For better or worse, humans have become a geological force. We've altered the atmosphere's composition faster than any volcanic eruption. We've driven extinction rates to levels not seen since the asteroid impact. We've carved mountains, drained lakes, turned forests into deserts, and deserts into cities. Future geologists, if any exist, will see a distinct layer in the rock record marking our time. Plastic, concrete, nuclear isotopes, chicken bones, bizarrely enough. The Anthropocene will be visible millions of years from now, a thin band of evidence that something unusual happened on Earth in the early 21st century. The question is what comes next, not in billions of years. That's predetermined. The sun will swell, the oceans will boil, the planet will die. Nothing we do changes that end point. But the next few hundred years? The next few thousand? Those are ours to write. We can continue as we have been, consuming, expanding, treating the planet like it owes us something. Or we can recognize what the timeline shows us. Earth is resilient, but it's not indestructible. Species go extinct, ecosystems collapse, civilizations fall. It's happened before, it'll happen again. The dinosaurs ruled for 135 million years and left nothing but bones. Humans have been here for 200,000 years, and we've already sent machines to other planets, split atoms, sequenced our own DNA. We've achieved more in a geological eye blink than any other species in Earth's history, but we've also created problems no other species has faced. Climate instability, nuclear weapons, ecological collapse. The tools that make us powerful are the same ones that could end us. And unlike the dinosaurs, if we go extinct, it won't be because a rock fell from space. It'll be because we couldn't figure out how to live on the only planet we've got. But maybe we will. Maybe the next chapter isn't catastrophe. Maybe we learn to balance growth with preservation, technology with sustainability. Maybe we spread beyond Earth, becoming a multi-planet species before the sun makes this one uninhabitable. Maybe future humans, or whatever we evolve into, look back at the early 21st century as the moment we chose differently. The moment we stopped treating Earth like an infinite resource and started treating it like what it is, a rare, precious anomaly in a mostly dead universe. Or maybe we don't. Maybe we're just another layer in the rock, sandwiched between the Cretaceous extinction and whatever comes next. Maybe some future species evolves intelligence, digs up our fossils, and wonders what we were. Maybe they make the same mistakes. Maybe the cycle continues until the sun finally ends it all. Either way, Earth keeps spinning, continents keep drifting, the moon keeps pulling tides. The universe doesn't care about our choices, but we do. And that's enough, because even if we're a blip that knows it's a blip. We're matter that became aware of itself, looked around and asked why. That's rarer than you think. In all the planets we've discovered, all the galaxies we've mapped, we haven't found another species doing what we're doing. Maybe they're out there. Maybe we're alone. Either way, right now, on this rock, we're it. So here's the takeaway. You've seen the full timeline now. You know where we came from. You know where we're going. You know how fragile this all is, and how improbable. The next time you look at a mountain, remember it used to be an ocean floor. The next time you see a bird, remember it's a dinosaur. The next time you breathe, remember that oxygen used to be poison. Everything around you is borrowed time, rearranged matter from a planet that's been recycling itself for billions of years. And you're part of that. Your atoms came from dying stars. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all forged in supernovas billions of years ago. You're not separate from Earth's timeline. You're in it, a brief bright moment in an incomprehensibly long story. Make it count, because the planet will be fine. It survived worse than us, but we only get one shot.